Imagine you wake up in a room. There is nothing in it except a computer and a router. You need to reach someone for help. So you open the browser and type facebook.com. But wait, how do you actually know that's Facebook? You don't control the network. The router in that room could be doing anything with your request. In fact, it could even intercept your DNS request and redirect you to a fake website that looks exactly like Facebook. It sends you the IP of a malicious one, a fake website, pixel perfect that looks exactly like Facebook. You would have no idea. And even if the website were real, anyone watching the network could see everything you send. Your messages, your passwords, your credentials, everything. So we have two problems, trust and privacy, and both needed to be solved. Let's tackle privacy first, and that means encryption. There are two types of encryption you need to know about. The first is symmetric encryption. Both sides share a single key. That key encrypts the data on one end and decrypts it on the other. It is fast and efficient, great for a large amount of data. The second is asymmetric encryption. Here you have two keys, a public key that anyone can have and a private key that only you hold. Data encrypted with the public key and can only be decrypted with the private key. It is more secure for certain use cases, but it is significantly slower. So, which one do we use? Both. And here's why that's clever. Asymmetric encryption is used first just to securely exchange a shared symmetric key between the two sides. Once that key is delivered safely, all the actual communication is encrypted using the faster symmetric algorithm. You get the security of asymmetric encryption for the key exchange and the speed of symmetric encryption for everything else. But here's the thing, encryption alone doesn't solve our first problem. Even if everything you send is encrypted, you could still be sending it to the wrong person. You could be encrypting your messages perfectly and handling them straight to an attacker. You still need to know who are you actually talking to. So when you visit our website, you explicitly say,
Wait a minute! Who are you?
and this is exactly why certificates exist. Think of a certificate like a passport. When you cross a border, you don't just tell the officer your name and expect them to believe you. You hand them a document issued by a trusted authority, stamped and verified. That proves who you are. The officer trusts the passport not because they know you, but because they trust the government that issued it. A digital certificate works the same. When your browser connects to a website, the website hands your browser a certificate. That certificate says, I'm Facebook. And more importantly, it is signed by a trusted authority called a certificate authority or CA. In other course in video, we will see how signing is made using cryptography. Now, back to our room scenario. If the router tries to redirect you to a fake Facebook server, that server would need to present a valid certificate from facebook.com. But it can't. It doesn't have one. Certificate authorities verify ownership before they sign anything. In normal circumstances, it cannot get a legitimate certificate for a domain it doesn't control. Your browser would immediately show a big security warning and block the connection. So, a certificate answers a simple but critical question. Is this really who they claim to be? And inside that certificate is also the website public key, which brings us back to encryption. Once your browser trusts who it is talking to, it uses that public key to securely kick off the encrypted connection we described earlier. Let's make this concrete. Here's the Facebook website open a browser. If we click the padlock in the address bar and inspect the certificate, we can start reading what's actually inside. The subjects tell you who this certificate belongs to. Facebook.com, for example. This is the website identifying itself to your browser. The issuer tells you who signed and vouched for it. A certificate authority. This is the trusted third party we talked about. The validity period shows you the window the certificate is active. These are typically short anywhere from 90 days to a year, because the shorter the window, the less damage a compromised certificate can do. The public key is what your browser will use to kick off the encrypted connection we described earlier. And then there is a field worth pausing, the subject, alternative, name, or sign. This lists every domain this certificate covers: uscmessenger.com, facebook.net, m.facebook.com, and several others. Now, this field is interesting beyond just technical purpose. Bug hunters and security researchers pay close attention to it during reconnaissance. Companies sometimes list staging environment, internal subdomains, or lesser known panel inside the SAN without thinking much of it. Things that are not publicly advertised but are sitting right here, visible to anyone who inspects the certificate. So if you ever do a recon on a target, the SAM field is worth checking. And of course, there are more fields of different use cases. Now, you will notice something. The certificate Facebook present isn't the only one. There are actually three certificates here. But before we look at them, let's understand why this chain exists in the first place. Imagine that the certificate authority had to personally sign every single certificate for every website on the internet. Millions of certificates all tied directly to the most sensitive key in the entire system. If that key ever got compromised, everything signed by it would be compromised too. The entire trust system collapsed. So instead, CA don't work alone. They build a chain. Let's see how this works in real life. To create any certificate, the process starts the same way. You generate a private key, then you combine that private key with the subject information, who you are, validity date, and so on. But what makes a certificate trusted in the signature on it? And that signature comes from the private key and certificate of whoever is above you in the chain. That's what binds everything together. At the top, you have the root CA. It generates its private key, combine it with its own identity information, and sign it with itself. Because there is nothing above it. This produces the root certificate, a self-signed certificate that can be pre-installed in your operating system and browser. On Windows, you can see this root certificate yourself by opening the Certificate Manager. Just run cert mgr.msc in the Run dialog. Under Trusted Root Certificate Authorities, you will find every root CA your system already trusts, hundreds of them, shipped with Windows and updated through Windows Update. On Linux, they are stored as plain certificate files, typically under /etc/ssl/cert or other directory. You can open any of them and read the feed we talked about directly. As for browsers, Chrome and Edge on Windows lean on the operating system certificate store, so they trust wherever Windows trusts. Firefox is different. It ships with its own independent certificate stored, completely separate from the operating system. You can browse it yourself under Setting, Privacy and Security, View Certificates. Same idea on Linux. Firefox maintains its own store regardless of what's in Linux system. That's the starting point of trust. You already have it before you visit any website. So when your browser receives a certificate chain from a website, it is checking the root of that chain against one of these stores, either the operating system store or its own built-in one dependent on the browser. If the root is there, the chain is trusted. If it is not, you get a warning. Now, the root uses its private key and its own certificate to sign a new one, this time for an intermediate certificate authority. The intermediate gets its own generated private key, its own identity information, and the root signature on top. That signature is what gives the intermediate its authority. The root saying, I vouch for this entity, and anything it signs carries my trust. When Facebook wants a certificate, they generate their own private key, combine it with their domain information and public key, and send it to the intermediate certificate authority to be signed. The intermediate signs it using its own private key and certificate, producing Facebook's entity certificate. Now, if you look at the validity field across all three certificates, you will notice something. The further up the chain you go, the longer the validity period gets. Facebook's end entity certificate might be valid for 90 days to a year. The intermediate says somewhere around a few years, and the root can be valid for 20 to 25 years. This makes sense when you think about it. The higher up the chain, the harder and more impactful it is to regenerate and redistribute that certificate. The root especially, it is embedded in billions of devices worldwide. You don't want to rotate that frequently. But at the bottom, short validity means that even if a certificate is compromised, the damage window is small. So your browser works this chain from bottom to top. Facebook's certificate was signed by the intermediate was signed by the root, and the root is already sitting trusted in your system. Every signature verifies, every link holds, connection proceeds. Now, let's think about this from an attacker's perspective, because that's where the real value of this chain becomes clear. Say an attacker managed to steal Facebook's private key. That sounds catastrophic, and it is, but the damage is actually contained. With Facebook's private key, the attacker can impersonate Facebook.com. They can present Facebook's legitimate certificate and use the stolen keys to complete the handshake convincingly. Your browser sees a valid certificate, a valid signature, and trusts the connection completely, at least until the certificate is revoked. But that's where it stops. They can only impersonate Facebook. They can't force certificates for Instagram.com or Google.com, even ones that use the exact same certificate authority. The certificate itself was issued specially for Facebook.com, and no private key in the world lets you change what's written and signed inside it. Now let's go one level up the chain. If an attacker gets the private key of an intermediate certificate authority, say let's encrypt intermediate, the situation becomes significantly more dangerous. Now they are not just impersonate one website, they can issue certificates for any website that changes to that route and passes client validation rules. They could generate a brand new trusted certificate for Facebook.com even though Facebook normally uses DG certificate authority. Your browser doesn't care. It walks the chain, finds a trusted route at the top, and accepts it without a single warning. And if somehow an attacker reaches the root certificate authority private key, the impact is total. Every certificate under the root across every intermediate and every website that chains back to it is now forgeable. That's why rootkeys are treated with extreme care, stored offline in hardware security models, sometimes in physically secured facilities. The root is almost never used precisely because the consequences of losing it are irreversible. So the chain isn't just about organizing trust, it is about containing damage. The higher up the compromise, the wider the blast radius. And that layered containment is exactly what keeps the internet's trust model from collapsing. With today's technology, there is no practical way to derive a private key from a public key. Modern cryptography is designed to make that computationally impossible. The only serious long-term threat is quantum computing, which is why I'll cover post-quantum cryptography in a future course in video. So, what we just walked through, the root certificate, the intermediate, the signing process, and the trust verification, all of that belong to a larger system called Public Key Infrastructure, or PKI. PKI is simply the framework that allows digital certificates to be created, distributed, validated, and revoked at the internet scale. And the HTTPS connection your browser makes every day is powered by it. So that layer padlock in your browser isn't just encryption, it is a global trust system built on certificates, signatures, and carefully designed chain that start at a trusted root. Every connection is verified, every link is checked, and that's why HTTPS works. But understanding the system is half the story. In the next video, we'll break it in a lab and see what happens when someone tries to fake that trust. I'll see you there. Bye bye.